Hey everyone, on this lesson we will study in depth the principal component analysis technique. Remember that on the previous lesson we introduced this technique that allows us to analyze very large data sets containing a high number of dimensions. It also increases the interpretability of the data while preserving the maximum amount of information. So formally, this PCA is a technique for reducing the dimensionality of the dataset. Principal component analysis has applications in many fields such as population genetics, microbiome, and atmospheric science. So let's start studying this technique and see how it works. Initially, given a dataset, we assume that this dataset and the attributes and the features of this dataset follow a Gaussian distribution. Keep in mind that Gaussian distribution is another term for normal distribution. Also, the global variance on the dataset is preserved, that is, of the variance for all the attributes from the dimension 1, this is the feature 1 of the dataset, until the dimension d, this is the total number of dimensions, the total number of attributes, the total number of columns in this dataset. Then the global variance before applying the principal component analysis technique is the same as the global variance after applying this principal component analysis technique. In PCA, the data is projected onto a set of orthogonal dimensions that they are the components. These components are linear combinations of the original attributes. So once we have initially the data set, we have the data, we project this data onto a set of orthogonal dimensions. These dimensions are called the components of the PCA, and they are linear combinations of the original attributes of the data set. So here we see a representation on how we can calculate this new dimension y. This orthogonal dimension y is nothing more than the linear combinations of the original attributes. Here the original attributes are this x with subindex d. We know that this dimension is orthogonal, as we see in here, since for each pair of dimensions that we have on the PCA, they will form an angle of 90 degrees, which is a perpendicular angle. Now, the transform dimensions in PCA are uncorrelated. Remember that correlation in statistics is any relationship, whether causal or not, between two random variables. So on the PCA technique, these dimensions, transform dimensions, are uncorrelated, they have no correlation, but also they are not independent. So since we know that the correlation, since they are uncorrelated, there is no correlation, then this covariance is equal to 0 for two pairs of these transform dimensions. So we can see here that this first y with subindex I is the first transform dimension. This second y with subindex j is another transform dimensions. And this is true for any pair of transform dimensions. Something interesting also to know that we can sort these transform dimensions by the information of their variance. So for instance, if the transform dimension y1 has the biggest and the largest variance, then we can sort them in decreasing order in this way, so that we can put identifiers. So here we have the identifier y1 because this is the number one variance, the one that has the biggest variance. This is y2, it is the second with the biggest amount of variance, and so on. Now, this PCA technique computes a projection matrix. For those who don't know, the projection matrix in statistics maps the vector of response values, these are the dependent variable values, to the vector of fitted values, or also named as predicted values. The matrix describes the influence each response value has on each fitted value. So on the PCA, this projection matrix scales and rotates the data to the new orthogonal dimension space. Keep in mind, here we have the new transform dimension and the second new transform dimensions. Keep in mind that they are perpendicular, right? They are orthogonal. This will always be like this. They will always form an angle of 90 degrees. So to calculate PCA, there are several ways to derive this method. On this course, we are going to explain the method based on the maximization of variance. So let's begin. We have initially, and suppose we have a data set with a given number of attributes. This data set has been standardized. This means that all the attributes, all the features are centered and they have unit variance. Their variance is 1. Their covariance can be defined in this way. So then we assume that there is at least one dimensional space U with dimensionality M less than D defined by a projection matrix B. So when we make the transpose of this projection matrix multiply with this attribute, we have this dimension. And we define B as this projection matrix. Keep in mind that the dimension of B is a matrix that has a total number of D rows and N columns, where the columns of B are perpendicular and also unitary. So you can see this as each value B with subindex I is a base of the space U. This projected data we denoted with this X, with this arrow point, with a subindex N. This projected data obviously will belong to this dimension U, and the coordinates with respect to the base U as Z of N, which is this Z. This Z of N are the coordinates with respect to the base of this dimension U. So here the objective is to obtain the base vectors B and their coordinates Z, so that the projected data is as similar as possible to the original data. Also keep in mind, since we have standardized this data, so the data is centered, the mean of this Z is also going to be 0. So we start by looking for the first vector B1 that belongs to the dimension and the set of dimensions D, such that it maximizes the variance when projecting the data. So when looking for this first vector B1, we want to maximize the variance of the first coordinate Z1, right? Where the variance of Z1 is defined like so. And we also have that the first component Z1 of Zn is given by this notation, which is here the product of the transpose of the vector B1 multiplied with the Xn. So here we can just substitute this Z1 squared to this. If we know that Z1 of N is equal to the product of B1 transposed with Xn, so the variance of Z1 is going to be all this with square value, right? So when we make the square of this is the same as multiplying the same for the same. So at the end we have this final expression. However, don't worry for these formulas, since we will do this in this course all in Python. And in Python, there are methods that we can invoke and they do all this work for us. So here we are only introducing the mathematical notation and the mathematical foundations of this, because it is important to know, but in reality when we start applying the principal component analysis in datasets in Python, we will do it with procedures that are already predefined. We will do this in the practical part of the course. We are currently in the theoretical section. So now if we want one unique and only one single solution, to ensure that we only have one unique solution, we need to have the restriction that B1 needs to have length 1. So the problem we must solve is this one. We want to maximize the variance subject to this restriction, which is precisely that the length of this vector is 1. And this is basically a constraint optimization problem that can be solved using Lagrange multipliers. Again, we are basically looking at the mathematical point of view of this problem and how we can solve it. Remember, to solve this Lagrange, we need to calculate the partial derivatives over the arguments, right? We have here two arguments. We have b1 and lambda, so we calculate the partial derivative of this function as respect to b1 and also as respect to d lambda 1. And then we equal these equations equal to 0, right? Because we want to find the maximums. And this solution corresponds to the eigenvector of the covariance matrix that we represent with this summation symbol. And the Lagrange multiplier lambda 1 is the corresponding eigenvalue. So here remember that an eigenvector is a linear and a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. And the corresponding eigenvalue, often denoted with lambda, is this factor by which the eigenvector is scaled. So this is merely for formalization. If we have a linear transformation T from a vector space V, and V is a non-zero vector, then if this value T of V is a scalar multiple of V, then V is the eigenvector of this linear transformation T, and lambda is this scalar known as the eigenvalue. Okay, this is a very linear algebra concept and very known. So with this information we can continue. So this allows us to substitute in the goal that we are optimizing. So now the variance of Z1 is equal precisely to lambda 1. This Lagrange multiplier, which is the eigenvalue. So all in all, this means that to maximize the variance of the first vector b1, then we must choose the largest eigenvalue of the covariance matrix and use its first eigenvector. This is going to be the first principal component, this first eigenvector that we find. And so to find the rest of the components, we can proceed in the same iterative way, subtracting now the effect of the previous n-1 components, and then imposing that the new component must be also perpendicular to the last component, the last eigenvector that we have found. Keep in mind that all the components here, right, are orthogonal. And so, in the end, we obtain that the components correspond to the eigenvectors of the covariance matrix, and the sum of the eigenvalues is going to be the total variance. Where this Greek lambda, this is another Greek symbol to represent lambda with another notation, this is a diagonal matrix. Remember that a diagonal matrix is a matrix in which the entries outside the main diagonal are all zero. So we really only have elements in the diagonal, and this lambda is going to be the diagonal matrix with the eigenvalues, and B is going to be the eigenvectors. As we can see here, B, each value of B, each element in here is the eigenvector. So here we can see a quick example. We have here original, these two dimensions, we have this original data. We apply the principal component analysis, and now we find the first component along the maximum variance of the data. Once we find this component, this eigenvector, as we can see here with the arrow in red, now we continue in a iterative way with the principal component analysis, and then we find the next component. Keep in mind that this next eigenvector needs to be orthogonal, needs to be perpendicular to the previous one, and this happens also in here. And this is the maximum variation vector perpendicular to the other components. So again, this lesson is all about the theory behind the PCA, behind this principal component analysis. It's all about mathematics, really. In this lesson, we are now inside the code in Python on how to implement this. We do this on the practical section of this course. where we apply the PCA with different data sets and see how we can do that using Python. So for this lesson, as a conclusion, if you're using a mathematical notation, right, keep in mind that since the eigenvalues correspond to the total variance, then it is possible to calculate the proportion that each component represents as the division of the eigenvalue I divided by the sum with all the eigenvalues. Also, to establish a stop criteria, we can decide the threshold. We can set a threshold, basically representing how much variance we want to keep. For instance, 90%, and we will discard the remaining components. Also, we can represent the variance of the components in decreasing form. This is commonly known in machine learning as a script plot. A script plot is a line plot of the eigenvalues of factors, or also the principal components in an analysis. Why is this script plot used? Well, this script plot is used to determine the principal components to keep in a principal component analysis. We will talk more about this on the practical part in this course and how we can interpret these script plots. So finally, if we take 2 or 3 components, we can visualize the data, because we know it is possible to visualize the data in 2 dimensions and also in 3 dimensions, right? Now, the quality of this visualization depends mainly on the amount of variance of those components. So we will study many examples, we will see many examples on this in the practical section of this course, where we will apply this PCA technique, the principal component analysis in Python. Very well. So for now, this is all about the theory that you need to understand and to know, and really to have a quick idea to start implementing the principal component analysis with real data sets in Python. So now just jump on the practical section and we will begin programming in Python.